fresh module, that is nothing but module number 4. So in this module number 4, so what we are going to discuss is, see in the module number 3 what you module number 1 what you have discussed is, so we discussed about some of the preambles of the VLSI technology. So what do you mean by preambles of the VLSI technology? We discussed about the history of VLSI technology, when an IC fabrication has been started, what are the different of IC fabrications are there, okay, and how we are going to design an NMOS transistor, PMOS transistors, what the different process you are going to involve in the fabrication process, that is nothing but NVL fabrication process, FEVL fabrication process, and BiCMOS technology. Okay, so that we discuss in the module number 1. And so once we know how we can able to fabricate the basic transistor circuit, that is nothing but NMOS and PMOS, in the second chapter what we discussed is, so how we go about the implementation wise. Okay, so in the second module we went for the that is the lambda based design rules, and we went for the layout masking, that is a layout diagram we went. Okay, so means what, if I able to implement or if I able to fabricate the NMOS transistor, then how best I can do the fabrication process. So how you get to know, by the use of this lambda based design rules. So we learned about the stick diagram. So when you want to implement your, or when you want to fabricate any one of the MOS transistor by using a VLSI technology means, then you need to know the layering architecture of the implementation. So how the NMOS has to be designed, how the PMOS has to be designed, how you differentiate between the NMOS transistor and PMOS transistors. So for all those things, so we have set up a standards, and those standards we call it as a lambda based design rules. So the ultimate goal of this lambda based design rule is to create a mask layout. Okay, so is to create a mask layout. So that and all things we discussed in the module number 4. So means what, so as we are completing the module 1, module 2 and module 3, so we are going from component level to the application level, or we are going from component level to the circuits level. Okay, so that is what you have learned in the module number 2. And in the module number 3 what you have learned, so we learned about how we can implement a little circuits or a fundamental circuits by the use of the basic elements. So that is nothing but CMOS, NMOS, inverters. Okay, so PMOS transistor, NMOS transistor, and the inverters, buffer. So one simple example what we can do is, in the module number 3 we discussed about the adders. So basically first we discussed about the adder. So what do you mean by half adder? So how I can implement that half adder? So what are the different types of adder circuits I can implement? So that you discussed in the part A of the module number 3. And then what we went, so we have extension of the adders we went, that is nothing but ALU we implemented, that is nothing but a arithmetic logic unit. So before we go for ALU, we learned something, two important concepts. The one we call it as a data path model, and one more we call it as a control path model. So in the data path model what we have learned is, basically, so when two subsystems, so let's say one adder is there, one bit adder is there, and one more one bit adder is there. So if I want to have a communication, or if I want to have a data transmission between each module wise entity, so how the data will flow from one entity to another entity, we call it as a data path. So that we discussed in the module number 3. And one more important thing we discussed, that is nothing but a control path. See, it's not that all the elements will be multiplied or added successfully. So sequential operations will take place in the any one of the circuit implementation. So the signaling mechanism or controlling of each operations from the fundamental units we need to do it. So for that we will be using a control signals. Okay, so that is nothing but a control bus we will be using. And then we went for the ALU design or the implementation. So there are different varieties of ALU implementations we have done. So in that ALU implementation, we discussed about the adder circuit, that is nothing but the implementation of a half adder. And then we went from implementation of a half adder to full adder, that is nothing but full adder implementation by using two half adder circuits. And then we went for the carry ripple adder, and we went for the carry skip adder. Okay, so all those things we discussed in the module number 3. Okay, so in this module, or what we are going to do is, the extension of your module number 3 will be studied in the module number 4. So that is nothing but subsystem design. So in the module number 3 only we discussed about what are the different design procedures are there and what are the different entities you need to consider. So all those entities application part you are going to study it in the module number 4. So in this module number 4 again we have two different subsections. So in the first subsection we discussed about design aspects of the subsystem, and in the one more chapter of this module number 4 we discussed about we will discuss about a FPGA based system. Okay, so in the first chapter of your module number 4, so we study some architectural issues. So what are the architectural issues we need to consider when you want to design your system, and what you mean by switch level logics you are going to study, and the gate level logic, that is nothing we call this gate level logic as also a restoring logic. Okay, so that you are going to study in this module number 4, and you are going to study about priority generators and multiplexers you are going to study, and the extension of these multiplexers we call it as a programmable logic arrays you are going to study, that is we call it as a PLA circuits we are going to study. So means what, as the we are moving from module wise to module, the complexity of design we are able to increasing, and we are able to understand how the complexity is there and what are the different things we need to consider when we design these components by using a fundamental element. So that was all about your module number 4, that is a chapter 1. And in the next section what we discuss is we discuss the implementation part. So means what, is there any platform is there for us to do, or is there any already available kit is there so that I can directly dump my fabrication process or implementation process. So for that we are going to study in the VLSI technology, that is nothing but FPGA, that is nothing but field programmable gate arrays. So the field programmable gate array circuits will enable us to realize your circuits in a hardware component. Okay, so you're going to study about the architecture component of your FPGA based system. So how actually the FPGA has been evolved. So what are the different options of creating or what are the options of your using your system implementation in a FPGA past. All those things you're going to study in this second chapter of the module number 4. So you can see here you'll be studying about the basic concepts, how you can going to implement your circuits, and you will be studying about the FPGA architecture and the physical designs of your FPGA, and the data flow modeling, that is the VLSI or whatever we are going to, you studied about already HDL programming skills, no? So you'll be going for RTL logic, TTL logic, and you'll be studying about LUT tables. So what do you mean by LUT tables? So how this will up different from truth tables. So all those things you're going to study it in this FPGA based subsystem. Okay, so these are the things what you're going to study in this VLSI chapter in the module number 4. Okay, so the first thing and the fundamental thing what you need to understand is the architectural issues. So what do you mean by the architectural issues you need to see? Okay, so because the ultimate goal of any designer or any engineer is to get the best from scratch, or we call it as it should be free from errors. Okay, so whatever the design methodology you are going to consider, whatever the architecture you are going to consider for the implementation of any circuit, it should be minimum to prone errors, or it should have a minimum environment to be affected by the external entities. So that we call it as architectural issues. So what are the entities or what are the parameters which will constitute in this architectural issues has been listed over here. So the first thing is in the defining of your requirements. Okay, so before you select any architecture for your implementation, what are the requirements you have, you need to be defined very properly and carefully, and it has to be elaborated. So what are the entities you are going to consider primary, what are the requirements? So let's say you want to design an elevator. Let's say one simple example I will give you. So you want to design an elevator. So the first thing what you need to consider, what is the capacity, that is the number of users that it wants to carry. So that you need to see it out. And what is the height that the elevator you want to design, that you need to see it out. Okay, and then what is the speed of the elevator you want to design it, and then what are the implementation architectures you need to incorporate. okay, and what is the power constraints over that, where you are going to locate your elevator, that has to be checked. Means what? The basic requirements, the requirements which you are going to do before implementation, it has to be analyzed carefully and properly. So that is the first architectural issues, what we call it as, that is nothing but defining of the requirements. The second, we call it as a partition the overall architecture into appropriate subsystem. See, I told you the elevator concept. So this elevator concept that you cannot write, okay, I know the MRO, I know the VHDL, or let's say I know the system very long. So directly I will go for the implementation, or so directly I will start coding which is related for the, which is needed for the elevator mechanism. No, it is not the thing. So when you take up any complex problem, or when you take up any problem, engineering problem or real-time problem, it has to be understood first, and then it has to be divided into subsystems. It has to be divided into subsystem. So each subsystem should work on one functionality. So if you implement that functionality properly first, and if it is, you need to test for that functionalities. So if you are getting the result, favorable results according to you, means then you need to go for one more subsystem implementation. So if you're getting the result for the second subsystem properly, how you want it, then you go for the third implementation. So means what? The unit by unit implementation is necessary in the VLSI architecture. So that we call it as a partitioning the overall architecture. When you want to do the partition, you should be very careful that, so how the communication and entities is been having a relationship between from one entity to another entity, you need to understand. Okay, so that you are supposed to understand in the partition of the overall architecture. The third one, as I told you, the communication path. So I told you, you need to divide the system into subsystem. So when you divide the system into system, so how these subsystem will communicate, what are the data path you are going to establish between two subsystems, or what are the controlling signals are necessary, whether these subsystems should be operating concurrently, or whether these subsystem need to be sequentially operated, and who has to have a control on these subsystem, who has to do the controlling mechanism for this subsystem. Okay, so all those things has to be communicated properly between the subsystem. That is nothing but the establishment of communication path between two subsystems need to be understood properly, and it has to be analyzed properly before we go for the actual communication between the two subsystems. That has to be done. The next one, we call it as a floor planning. So this is a very important things before you go for the fabrication. Okay, you have designed the system, and you have implemented by using a Verilog program, and you got a RTL logic. Okay, so everything you got a circuit. Now when you want to implement this practically, the floor planning is an important mechanism. So as I told you, this floor planning, what it does is it creates, or it will enable you to place your component so that you can minimize the size of the IC. Okay, so if you design, or if you choose a floor planning in such a way that the circuit area which will be taken by, or it will be implemented by any particular application, if it is minimum name, then we can say that the design considerations has been achieved successfully, or else it has to be reworked again so that the constraints in the size can be minimized. So that all issues will come under a drawing of the floor plan. So how the power supply has to be there. So if the where the power supply location has to be there. So if the power supply location has to be very near to the modules, means then how the wiring you are going to do it. So all those things you need to be understood. Okay, so the next one is as we study about one of the important parameter, we studied about the regularity. Okay, so the regularity is also plays an important role in the VLSI subsystem. So if you want to design in any IC, or if you want to design in any circuit, the regularity of the circuit the regularity of the circuit has to be high as possible. Okay, so the next one, we call it as a, that is a stick or a symbolic diagram. So always the subsystem are representation of your leaf cells. It should not be a main part of the architectural methodology. So whatever the subsystem you are going to design, or whatever the subsystem you are going to create, all them has to be a leaf cells. Okay, and the next one is simultaneous. That is nothing but a simulation. You need to understand the performance of each subsystem. That is how you need to do it. Okay, So this is one of the simple switch level logic what we have considered. That is nothing but it is a serial input what we have taken. You can see here the VIN is being connected to 3 NMOS transistor. There is 4 NMOS transistors. You can see here A, B, C, D. So depending upon the A, B, C, D values, so whatever the input is there, right? So it will be attached to your output section. So you can see here the driving capacity of your V output, it mainly depends upon the 4 transistors. So that is nothing but the transistor number A, transistor number C, D and B. Okay, so you can see here your output will be equal to input when A, B, C, D all are is 1. So we call it as an AND logic implementation. Why? Because so since all the input terminals you are given the NMOS transistors, so if the NMOS transistor has to be work properly, means then the gate terminal has to be applied as stable positive voltage. So therefore when A, B, C, D all are 1, so that is nothing but ANDing operations we are implementing in this switch logic. So if A, B, C, D is equal to 1 means then what we get is it like act like a buffer. Okay, so now the buffer has to be converted if we want to do it in the inverter. So the buffer has to be negated. So in order to do the negation, what we can use is we can use a inverter at the output of the V out. So if I use the inverter at the output of the V out, what you'll be getting is you'll be getting a negation of the input terminal. So therefore, in order to get the negation of the input terminal, we will be getting a V out. And sometimes what happens is in some circuits we require an the delay elements has to be rechanged, or we need to introduce a delay in the signal propagation. So if you want to introduce a delay in the signal propagation means then we use a buffer resistors between one entity to another entity. So that is how you are going to using over in the second diagram. And the third diagram what we call it as a transmission gate. So why we want to create this transmission gate is in order to improve the stability of the network, or in order to improve the signal propagation stability over the VLSI subsystem, we will be using this transmission gate. Okay, and the last one you can see here as a NMOS OR gate implementation over here is, so here we use the CMOS fabrication process. So you can see all the that is source regions all are coupled and the drain regions all are coupled, and parallel it has been converted into series. So it is nothing but a CMOS technology, and the corresponding V out we have written as V out is equal to A plus B plus C. And if you want to take the complement of that means then V bar V out bar by applying a De Morgan's law. So we can say that it is A bar into B bar into C bar. Okay, so this is the switch level logics what we are going to use for the implementation of the higher order circuits. So these are the things what you need to understand, so before we go for the complex circuits.